Have you ever wondered how air conditioners work? Stay tuned and you will find out. Before we delve into how air conditioners work, let's ask a simple question. When water boils, does it make the environment hotter or cooler? Intuitively, we might assume that boiling water makes the environment hotter because we need heat to boil water. But in reality, it actually makes it cooler. Think about it. Water boils at 100 degrees Celsius. It needs heat to reach that temperature before it can boil and turn into water vapor. That heat comes from the environment. This makes sense since we always need a heat source, such as a kettle or stove, to boil water. It's this heat which is being absorbed by the water to bring it to a boil. If this sounds confusing, think of what happens when ice melts. When ice melts, it has the same effect. It absorbs heat from its surroundings. As a result, putting ice in your drink makes it colder because the ice is absorbing the heat that's in the drink and hence lowering its temperature. We don't need an external heat source to melt the ice because the temperature of the drink is higher than the melting point of ice. The opposite happens when water turns from a gas to a liquid. When water vapor condenses to a liquid, it actually releases heat into the environment, thus making it hotter. This also happens when water freezes and turns to ice. To sum it all up, when a liquid boils and turns into a gas, it absorbs heat from the environment, thus cooling it down in the process. On the other hand, when a gas condenses to a liquid, it releases heat into the environment, heating it up in the process. Believe it or not, if you understand this, you've already understood how air conditioners and refrigerators work. To cool down a room, you need to boil a liquid and turn it into a gas using the heat that is already in the air inside the room. We can't use water since its boiling point is far higher than any room temperature. We need a substance that is a gas at room temperature, which means its boiling point must be far lower than room temperature. This gas is called a refrigerant. Let's imagine that a pipe passes through the room we want to cool. Now imagine that the liquid refrigerant is allowed to flow through the pipe at low pressure. While it flows through the pipe, it turns into a gas, because the temperature of the room is far higher than the boiling point of the refrigerant. Remember that when a liquid turns into a gas, it absorbs heat from its environment. This means when the refrigerant turns into a gas, it lowers the temperature of the air and hence the room. The refrigerant, which is now in gaseous form, continues flowing through the pipe and exits the room to the outside environment, carrying the absorbed heat with it. Effectively, this process moves heat from the room to the outside environment. However, we still have a problem. Once the refrigerant has turned into a gas, we can no longer use it to cool the room. This means we either need an infinite supply of liquid refrigerant or we need to convert the gaseous refrigerant back to a liquid. But how are we going to do that? It turns out there are actually two ways to convert a gas to a liquid. The way that we are most familiar with is to cool the gas down to its condensation point. However, we can also turn a gas into a liquid by compressing it into a small volume. Compressing a gas increases its pressure and forces the molecules to move closer together. Beyond a certain pressure, the gas can no longer remain a gas and is forced to condense to a liquid even at a high temperature. Compressing a gas also has another side effect. Remember that when a gas condenses to a liquid, it releases heat into its environment. This also applies when a gas is compressed to a liquid. This means we now have a technique for absorbing heat from the room, transporting that heat to the outside, and also for removing heat from the refrigerant. We have all the tools needed to build an air conditioner. A basic air conditioner consists of two units: an indoor unit that sits inside the room and an external unit that sits somewhere outside the building. The two units are connected by a closed loop of pipes through which the refrigerant flows. The liquid refrigerant is pumped through the pipes from the external unit to the indoor unit. An expansion valve inside the indoor unit ensures that the refrigerant remains in liquid form until it reaches the room. Once the refrigerant passes through the valve, its pressure drops and it is thus able to transition to a gas. A series of fans inside the indoor unit circulates the air inside the room over the pipes. While the liquid refrigerant boils to a gas, it absorbs the heat from the circulating air, thus cooling it down. The refrigerant, which is now in gaseous form, is then pumped back to the external unit where it is compressed back to a liquid using a compressor. This causes it to release heat into the outside air. This hot air is then blown away by a large fan. Finally, the liquid refrigerant is then pumped back to the indoor unit, and the process is repeated until the desired temperature is reached. Notice that the air around the external unit heats up while the air conditioner is running. This is the heat that was removed from the room in order to cool it down. For the air conditioner to work effectively, it needs enough air to dissipate the heat. Luckily, the Earth's atmosphere provides a practically infinite supply of air for dissipating heat. If the external unit were instead placed in a closed environment with a limited amount of air, the air around it will keep getting hotter and hotter as the room gets cooler. This shows that an air conditioner doesn't make the heat disappear, but only moves it from inside the room to the outside. Something neat about this process is that it can be reversed. Instead of moving heat from the indoor unit to the external unit, heat can be moved from the external unit to the indoor unit. In this setup, the liquid refrigerant is allowed to boil in the external unit, which causes it to absorb heat from the outside air. The gaseous refrigerant is then pumped to the expansion valve in the indoor unit. Once a high enough pressure is reached, the refrigerant condenses back to a liquid, which causes it to release heat inside the room. This allows an air conditioner to also function as a heater during winter. Heat pumps, which are a common alternative to traditional electric and combustion heaters, are just air conditioners running in reverse. Now you know that air conditioners cool rooms using a liquid that transitions to a gas. But did you know that this cooling process also exists in nature? You've probably noticed that the shade of a tree feels far cooler than the shade of a building. This isn't just an illusion. Trees actually cool their surroundings by the evaporation of water. Water is pulled in from the soil by the tree's roots, and then flows up the trunk to the leaves where it evaporates into the air. While evaporating, it absorbs heat from the air, just like the refrigerant inside an air conditioner. This means a tree not only provides shade from the sun's rays, but also cools down the air. A building, on the other hand, only provides shade from the sun, but doesn't cool the air. Thank you for watching till the end.